So we're going to move on to our next type of two-dimensional motion, and that's going to be projectile motion. So here we have a nice time lapse of an object going up through the air, exhibiting projectile motion, and so we're going to talk about how we analyze this type of motion. So far we've talked a lot about objects moving horizontally, whether it's cars, people, etc., speeding up, slowing down while traveling in a straight line. We've also talked a lot about objects going up in the air, and coming back down in free fall or vertical motion. What projectile motion is it's going to be a combination of this horizontal motion with this vertical motion. All right. Anything that's flying through the air, whether it's a football, a missile, a person jumping through the air, whatever it is, that's going to be an example of projectile motion. Okay, and any of those objects are going to exhibit motion both in the horizontal direction, all right, as they move through the air, and in the vertical direction. So the most important concept that we need to know about projectile motion comes from this one idea. And what I want you to think about to get at this idea is what forces are acting on an object while it's in midair. We have the force of gravity, okay, acting down, and since we're usually living in a frictionless vacuum here in Physics 1 AP, that's the only force. In reality, there is a little bit of air resistance, but we're going to assume that that air resistance is small enough that it's negligible. So the only force we have acting down is the force of gravity. So what does that mean about our motion, both horizontally and vertically? Horizontally, we see there are no forces. So that means, it doesn't mean the object's at rest, it means the object's moving at a constant velocity. Okay, it could be at rest, it doesn't necessarily have to be at rest though. Vertically, all right, the only force acting on it is the force of gravity, which is the same as an object just going straight up in the air and coming back down. So that means this object is accelerating down. Okay, and if we're on Earth, we can even say what the acceleration is going to be. It's going to be 9.8 meters per second squared. This vertical motion is free fall, what we talked about back in Unit 1. This idea right here is the most important thing that we need to know, or these two ideas are the most important thing we need to know about projectile motion. It's a combination of constant velocity in the x direction and free fall, or accelerating down at 9.8 meters per second squared in the y direction. So I have two pictures on this slide and the next that really show this concept. So if we look here, we have up first, we have the motion of an object. This is like one of those motion maps or dot diagrams showing the horizontal motion of an object with no gravity. So this would be, I always think of this as like the Wile E. Coyote running off a cliff. Before he looks down, this is what his motion would look like. Okay, in the y direction, we have the same thing. This is just showing the motion of an object in free fall, being dropped. Okay, not showing any horizontal motion. All right, and so we see that it is speeding up at a rate of 9.8 meters per second squared. This is what we get if we have an object rolling off of a table and undergoing projectile motion. And what we see is that path taken by the projectile motion is really a combination of this horizontal and this vertical. All right. So at this point here, there's its vertical position, there's its horizontal position. Then we have vertical and horizontal, vertical and horizontal. Those y coordinates and those x coordinates really combine to give us that parabola, that projectile motion that we see when an object rolls off of a table or is flying through the air. So projectile motion is simply a combination of this constant velocity in the x with free fall in the y. What we see here is simply a bigger version of the what we just saw in the last slide, okay, showing constant velocity in the x and free fall in the y. So a few implications of those two concepts. In the x direction, like I said, is pretty simple. Our acceleration is 0 because we are undergoing constant velocity. Keep in mind, going along with that, that only the delta x equation will be useful when we're dealing with the x direction. We've seen that before when our acceleration is 0. That VF and that VF squared equation don't really help us out. In the y direction, we have free fall, Okay, and that's really the most important concept, but there are a lot of sub-concepts, if you will, that follow from that. The first, obviously, is that our acceleration is 9.8 meters per second squared down. And then we also have all those other concepts that we talked about during Unit 1. The y velocity at the peak is 0, okay? The time to the peak is half the total time. Your y displacement is going to be 0, and your final is going to be the negative of your initial. Now, these three are only if it's symmetrical, okay? But all those concepts that we applied to free fall before, those are going to apply to the y motion of an object undergoing projectile motion, because in the y direction, it is free fall. It's identical. All right, so the equations we're going to use for projectile motion, turns out, are exactly the same as our kinematics equations. So these equations have not changed at all. They still describe accelerated motion, so they still apply. The only difference is we are now going to separate them into x and y. So two things about that. Number one, in the x direction, what I did was I took the delta x equation. Really, both of them will simplify to this, but if we get rid of that acceleration term and make it 0, we get a simplified version of this. Now, I don't have this on the equation sheet. This isn't something to memorize, but that's where that equation is coming from. Okay. In the y direction, we have the full 4 equations. The only thing that's different is I've added these subscripts, okay, just to distinguish between x and y motion. The equations are no different. We're just going to have to do them twice now because we have horizontal motion in the x and we have vertical motion in the y. This is just like doing F equals ma twice when we have both x forces and y forces. So it's no different than max and ma. We're just doing it with the kinematics equations instead of F equals ma. Okay, so there's going to be two types of launches that we're going to study when dealing with projectile motion. So I'd like to talk about how a few of these concepts apply to each type of launch. So the first thing that we can say, and this is going to be true for both kinds, we always know our accelerations are 0 and negative 9.8 meters per second squared. I'm usually going to make down be the negative direction, although if you made down be the positive direction, then that acceleration would be positive. But most of the time it's going to be negative, so I'll say it's negative 9.8 meters per second squared. With a horizontal launch, which is the first type of launch we're going to talk about, this is a situation where we're throwing the object horizontally. So maybe it's rolling off of a level table, maybe we're throwing it horizontally, but either way, it's moving horizontally at the instant that it's released. So that means one really important thing about our y velocity. It means that our y velocity, our initial y velocity, is just 0. Because if the object's moving horizontally, that means that it's not moving vertically at all. I'm now going to go ahead and just draw vectors representing the x and y velocity of this object at each point. So the x velocity, that is whatever that initial velocity is. And because it's constant, I'm trying to draw these the exact same length, that x velocity stays the same as it moves through. Okay, the y velocity initially is 0, we saw that, but then it is going to start picking up y velocity because it's accelerating down. So here it's going to have some amount of y velocity, here it's going to have even more y velocity because it's accelerating down at 9.8 meters per second squared. Having at least a conceptual understanding of the motion in both the x and the y is going to make things a lot easier when you're going to answer, especially some of these conceptual questions, but also some mathematical ones too. The other type of launch we're going to look at is an angled launch. So a few things with that. First of all, we know still that our x acceleration is 0 and our y acceleration is negative 9.8 meters per second squared. We see here in this case that we're launching it up at some angle, so this is not a case where our initial in the y is going to be 0. But we could find what our initial is in the x and the y based off of this initial velocity and our angle. We can take that initial velocity at an angle and break it into x and y components. This should be a habit at this point in time, that we're always breaking anything at an angle, any vector at an angle, into its x and y components. So my x velocity initially, which I'm going to call Vix, is going to be Vi cosine of theta, and my y velocity is going to be Vi sine of theta. And we're usually going to have the angle from the horizontal here like this, so that usually will be the same, but I guess we don't want to assume that that's always going to be the case. A few other really important concepts we know at the peak here, my y velocity is 0. When we get to that point, that's always going to be true. We also have a few ones that are true only if it's symmetrical. The first is that the time here is half the total. Okay, the second is when we return to the spot where we started, our y displacement is 0. Okay, and our y velocity is just the negative of our initial. So those were two concepts that were true when we had a free fall launch that was symmetrical, and they're also two things that are going to be true if we have a projectile launch that is also symmetrical. We're also once again going to think about our x and y velocity as it goes through its launch. So we have an x velocity here, looks something like that, and that once again is going to stay the same. Okay, we always have that same x velocity. All right, so all those arrows should be relatively the same length. In the y direction, we're starting here with some y velocity going up. When we reach our peak, we have no y velocity, as we talked about before. And then when we return to that spot, we have a downwards y velocity. And these two y velocities should be equal. Okay, so those arrows should be the same length. It's just that one's going up, the other's going down. When we return to that same point, okay, that same y position, we have the same velocities just going down then. And then obviously when it gets down to here, we have even more y velocity because it's accelerating. So this slide and the last slide really point out a lot of the important concepts you need to know about projectile motion. It all comes from this basic idea of what your x and y accelerations are, and the fact that we have constant velocity in the x and free fall in the y. But I think it's useful to kind of think through what that means about the actual motion if we have constant velocity in the x and free fall in the y. Let's go ahead now and apply some of these concepts that we just learned. So for this first question here, we have a baseball player hits a ball horizontally at 5 meters per second. So initially the baseball is traveling horizontally at 5 meters per second. It's going to travel some distance and eventually hit the ground here. And we have two questions. How fast is the ball traveling horizontally when it lands? Well, we know that in the horizontal direction, we have constant velocity. So it's still traveling at a speed of 5 meters per second when it lands. Our next question asks about the overall magnitude of the speed when it lands. Is it greater than, less than, or equal to 5? That is going to have to be greater than, because keep in mind, in addition to that 5 meter per second horizontal component, we also have a vertical component. And so the combination of those two is going to lead to an overall magnitude greater than 5. So the next one is asking about this cart that's rolling along a level surface like this, and it launches a ball straight up in the air. And we want to know when the ball lands, will it land in front of, behind, or directly on top of that cart? The cart's going to continue moving. So the thing to keep in mind here is immediately before that ball is launched, the cart and the ball are traveling at the same horizontal speed. So even though the ball's launched up in the air and it's going to travel through the air, at every single point it's going to have the same horizontal speed as the cart, because objects travel with a constant speed in the x direction. So that means it will always be directly above the cart, and it will land directly back in that basket. Okay? So in terms of a justification, I would just say that they both have the same initial x velocity, and they're both traveling at a constant speed, and that is making the assumption that the cart's traveling without friction. But in that case, it is going to mean that they travel the same horizontal distance because they're going at the same horizontal speed. So it will land directly in. This problem really displays the independence of motion of an object that's moving as a projectile. Okay, this y motion, that launch upwards in the air, doesn't affect the horizontal motion of the object at all. And so it maintains the same horizontal motion as the cart. For this next one, we have a conceptual problem where an object is launched with 20 meters per second of y velocity and 20 meters per second of x velocity. And then we want to know the time, x velocity, and y velocity of the object at a bunch of different points in time as it moves through its launch. Two really important things about this. Number one, we want to keep in mind that the dots shown here occur at even time intervals. So the time from here to here is the same as from here to here, and so on. And also, we're going to use 10 meters per second squared here for our g. I'm going to start with the easy one, and that is the x velocity. I know that my x velocity will always be 20 meters per second at every single point as it goes through this launch, because we have constant velocity in the x direction. So that will always be 20 meters per second. I also know that my y velocity at the peak here will be 0 meters per second, because that's what happens at the peak. That's one of our important concepts about an angled launch. Knowing that my y velocity here is 0, that actually helps me to figure out my time here. Okay, so I'm starting with 20 meters per second of initial y velocity, and by the time I get to the peak, I have 0. Keeping in mind that we're using g is 10 meters per second squared, all right, and thinking about the idea that that g is really 10 meters per second, okay, I'm going to lose 10 meters per second of velocity every single second. So the time it's going to take me to get to 0 is 2 seconds. That means that this is going to be 4 seconds, because the time when we return to where we started is going to be double the time to the peak. And then I can fill in this time, which is going to be 1 second, and this time, which is going to be 3 seconds, just knowing that these are even time intervals. Thinking about my y velocity, okay, I've already said that the y velocity at the peak is 0. I know my y velocity when I return to the spot where it was launched from, or to the height where it was launched from, is going to be 20 meters per second, but going down, right? And I can fill in the other two. So at this point here, all right, I can either think about the fact that it's been 1 second, so I've lost 10 meters per second of velocity, or I can think about the fact that it's going from 20 to 0, all right, and I know that this is directly in between, and it's losing velocity at a constant rate because our acceleration is constant. Either way, my velocity here is going to be 10 meters per second, and my velocity at this point is also going to be 10 meters per second, but just going down. And I can see here how there is symmetry about these 2 points as well. The y velocities are the same, just in opposite directions.